Hi everyone, this is Ben, one of the co-authors of this conference paper. Our work is a multi-agent deep reinforced learning-based voltage control on power distribution networks. This presentation is mainly divided into four parts. First, we will discuss the backgrounds, including machine learning and traditional voltage control. Second, the objective of this paper is presented. Then we give the proposed MADDPG-based control algorithm. Numerical simulation results are presented and a conclusion is given. The main task of the machine learning is to look for a function to approximate the nonlinear relationship with the help of deep neural networks and reinforced machine learning. Machine learning has been applied into speech recognition, image recognition, and Go game. What is machine learning? Machine learning is the field of artificial intelligence that uses statistical techniques to give computer systems the ability to learn from data without being explicitly programmed. So why do we need machine learning? There are four reasons. First, some problems cannot be explicitly programmed. Second, some scenarios are hard to model. Then, some problems need too many assumptions and simplifications. Finally, the environment is dynamic and uncertain. The type of machine learning are unsupervised learning, and reinforcement learning. The proposed method in this paper belongs to the field of reinforcement learning. Reinforcement learning learns a mapping function from stage action containing four essential elements, which are stage state, action state, stage transition probability, and reward state. The agent executes action according to received stage information and retrieve the instant reward and the next time step state provided by the environment. The target of the action is to learn the optimal place to maximize its cumulative reward. Deep reinforcement learning was first proposed to play Atari games, which are discrete control tasks. Then, deep reinforcement learning methods has been applied into other fields, such as famous AlphaGo. Go further, deep reinforcement learning can also achieve a good performance on a very complicated environment, for instance, AlphaStar, which demonstrates the powerful decision-making ability of the reinforcement learning. In today's smart grid, the voltage control in distribution network faces the following difficulties. First, the excess of renewable energy increases the uncertainty of the system and the variability of the voltage. Second, rapid fluctuations in PV power make it difficult for traditional methods to track in time. For large-scale distribution networks, the impact of delay is more significant. Traditional voltage control methods are robust optimization, heuristic algorithm, and probing-based method, but they suffer from the following drawbacks. For instance, the optimization results of the robust optimization are conservative. Heuristic algorithm is easy to stock into local convergence. A programming-based method requires a long calculation time and determine the distribution. To this end, we proposed a multi-agent deep reinforcement learning-based voltage control method, in which centralized training and the decentralized execution framework are adopted. After the training is completed, collaborative control based on local information can be realized to achieve real-time and fast response. The objective of this paper is to minimize the active and reactive adjustment while regulating the voltage as close as possible to the reference voltage over the time horizon. Here we give the mathematical expression of the objective and consequence. Next, the studied voltage control will be formulated as a Markov game. Specifically, agent is each PV inverter, and the environment is the whole power distribution network. The agent observations are the states of the located region, including active and reactive powers of loads and PVs, voltage magnitudes, and phase at time t. The reward function is a negative form of the objective function. Here we introduce a voltage barrier function to measure the voltage violation. The proposed method is the MADDPG algorithm. Here we present the implementation process of MADDPG, which adopts the forms of centralized training and decentralized execution. We also detail the network structures and settings. Three tricks are contained in this MADDPG method, which are centralized queue function calculation, decentralized execution, and target network updating. The objective of the centralized queue function calculation is to consider the coordination of the agents. Under the decentralized execution, agents can make decisions only based on local measurements. The target networks are to stabilize the training process, which are updated using a time delay form. In the numerical simulation, we first list the parameters of MADDPG, and the training process can be divided into three stages. First, before about 20 episodes, which is called exploration stage, the task of the agent is to gather sufficient experience by randomly exploring the stage and action spaces. As a result, the training results are not satisfied. During 20 to 300 episodes, the agent focuses on learning from the experience, namely learning process. The period of the last 100 episodes is a confidence process in which an optimized control policy is achieved. As seen, next we test the performance of the learner control policy on a test day. The 24-hour profiles of the PV generation and loads of the test day are presented. As seen, bus voltages under different control strategies are shown. Under the proposed control method, bus voltages are controlled within the voltage threshold, which demonstrates that the effective of the proposed method on voltage regulation. It can be observed that when no control strategy is applied, the voltage at bus 18 cross the safety limit during 220 and 260 times loads. Optimal power flow, drop control, and the proposed MADRL method controls the voltage within a safe range. Additionally, voltage overshot appears since drop control is a complete distribution control method without coordination between agents. The comparison results imply that the proposed MADRL method achieves the highest performance along the control methods. In this paper, we proposed a model-free MADDPG voltage control strategy based on decentralized training and distributed execution framework. The coordinated PV inverters control problem is formulated as a Markov game, and the DDPG algorithm is used to help each agent learn the optimal voltage control strategy. The training is carried out in a centralized manner, and agents make a real-time decision based on their local method. The effectiveness of the proposed voltage control strategy is evaluated on an IEEE bus distributed network. Meanwhile, the proposed method performance is further illustrated compared with traditional methods, which demonstrates the proposed method can adaptively solve voltage violations resulting from the emitter's nature of PV. Thank you.